Okay, welcome back. So now let's work in the same case, but now let's set up everything Fluent standalone. So at this point, you can close your workbench, but remember that you can explore here now. You can know where is the location of these files, these ones, these two. So you just need to copy the NSH files, okay, that you have for the mesh. Okay, so let me close here. Okay, yes, just to save. So I already moved the files here. I created a new folder. Okay, I call it my Fluent. I move one mesh here, and then also you can download here. In here, you can download the Fluent message or the settings. Okay, to run this case. So here I have the settings. Okay, so this we can use this setting to set up this case. Okay, it doesn't matter if you have you will see if we have different names of the patches or domain, but it will try this Fluent will read this setting and it will try to set up as much as it comes. So let's launch Fluent. Okay, so for instance, you have different names in the patches. It will set up those patches because the names are different, but then you can do it manually. What is important is that you see that setting Fluent properties, the monitors to sample, and that can be a little bit time consuming, and that information can be set up with no problem. So let me put here, this case is 2D, so now here you need to tell, so be careful. Okay, so we have here, we're going to read this mesh. So coming back to the website, so here you can download, remember, you can download the whole workbench, you can download the Fluent case files already set up to preset up, okay, then only the single mesh or the setting files, okay, or later we're going to do this one with the passive scalars. So first things, remember, scale, so here, open, sorry, read the mesh. Okay, so now that we have read the mesh, we can plot it. So see that we have the mesh. Remember also here in scale, so remember that you have the original mesh and we need to apply a scaling factor. Let me apply that scaling factor here. Scale, okay, and you can replot. And you have everything scaled already here. So always do this sanity check, verify everything, number of cells and everything. So at this point, remember that we want to read this settings file. Okay, I don't know why I call it settings squad. Okay, it should be just setting, but it doesn't matter. Okay, it's not. So to read that file, remember here you have the text user interface, and you can input basically everything that you do here, every click that you do here, you can access the same information here. And why do you have this? Because also you can run Fluent without this graphical user interface. So you can create scripts, and that is when you're doing, I don't know, parametrical studies, that is very, very convenient. Okay, you need to open your GUI, you have a text file that it will read here step by step what you want to do. That is a little bit more advanced, but just to let you know. So for instance, to read the setting files, you go here, File, you press enter, it will give you the options, and remember that we want this option, read settings. Okay, you can write the settings, you have it here, but we want to read settings. So to read settings, read settings, and then you give the name. So I call it settings underscore quad. And see that it's reading that setting file and it's applying everything that it was saved there. It is applying that to this current case. So even if the patches are, as I mentioned, you have these boundary patches with different names, it doesn't matter, you won't apply it because it's different, but the rest of the settings and everything that you create. So look at here that I created the custom field functions and everything. So this takes some time. So see here that everything has been already predefined. Okay, so you have, and this is very convenient. Okay, so let's go now and look at the case setup. It's pretty much the same as previous. So let me open here, see that I have a very specific line that is doing the sampling here. Okay, so let's revisit here. Okay, so see that models, enable energy, viscous, materials. If I go to materials, you see about water liquid. So cells on here, operating conditions, atmospheric pressure, Okay, as you go Fluent here and double click here, see that, okay, so here, see that it didn't apply the water liquid to this one because the name of the domain was different. Okay, so you need to apply it. And probably as you read here, you see that it will give you some warnings that you have different. See here that this one was skipped because it didn't exist. Okay, so it's telling you some information. See, so then boundary conditions. See, okay, by default put it in wall. So if I open this one, let's see what if we have right values. See that right values. So see in this case I use different values. Thermal 20. Okay, this one is also okay. Internal, this okay, this is all okay. So here also probably already apply my values. Methods already apply what was saved in that file. So see in this case I was using first order accurate for turbulence model, but the rest is second order accurate. So you have all the report definitions. See this one is telling that it's invalid because the name is different. So always check this one. Okay, so if you use a mesh with exactly the same names in patches, it's not a problem. But see, it's likely this name was different. So you just choose the right name and then everything should be fixed. Okay, then calculate everything is okay. So I want to show you something here. So residuals, okay, you have the residual, but I added another convergence condition. Okay, so sometimes people likes to add, for instance, a convergence condition in a coefficient, like lift coefficient. Here you have this in monitors convergence condition. So as you go here, okay, you can create those convergence condition. Okay, so in this case, see that I adding one is a temperature. So measuring report definition. So you need to create your report. Okay, so if you're using a force, just create the report for a force, and then here you put use the last 20 iterations, and when the difference is this one between those iterations, so it will use 20 iterations to measure that this quantity. Okay, when this different, you reach this tolerance, it will stop. Okay, so now you have this one, you need to reach both actually, and you will see when it's running. Okay, then honestly I have to say, yeah, some people like to put it, I don't like to put it. I always monitoring my solutions, but you will see how running, how it behaves when it's running. And at this point we can initialize. Okay, and by the way, for instance, you change all the boundary conditions, everything, you have the right names. Now you can save your setting file. So you can go right settings and you call it, oops, it's right settings, and I call it my set. Okay, so everything that you did here has been saved, and you will find it here. Okay, so now you can reopen it, pass it to another mesh. Remember, if you have a mesh with different names, okay, you are going to have problem there, so you can just fix it manually. So at this point, let me run, calculate, and see all the monitors we have here, and we have our residuals. Okay, so the residuals going down, 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 and you will see that here. Okay, let me go, now it's stopping. So see that solution for report definition 10 of half converge. Okay, so you reach this this convergence condition, but still you haven't reached the convergence condition for the residuals. And now see that you reach that condition, I will stop. Okay, so you can add it here to have a little bit more control. Okay, so as I say, I don't like to add those, but it's up to you. Okay, so you can add as many as you want. So now that we have the solution here, and in this case, our goal here in this one is setting the case in Fluent. We have seen everything, it's exactly the same workflow, but also let's do some more advanced quantitative and qualitative post-processing. Basically, I want just to show you these plots though, how we're done here. Okay, so the plot here, if I open here, see that I will go here, you have velocity contours. Okay, then I created, remember, all these plots were created in the setting files. You have your temperature there, turbulent viscosity. So remember, this is telling you where your turbulence model is kicking in or is generating, adding that extra ingredient. You go here. So at the walls, see that you select the walls and you're plotting there the y plus value. See that you can see that there. Okay. So you have an idea. So see that this mesh is not it's not optimal one. Your y plus values are about 10, are too close to the buffer layer. See that your average y plus value, in this case, it's reporting the maximum here. Okay, but for instance, you want to report the average y plus value, you can also compute it here. You have results, reports, surface integral, facet average, choose the wall and the quantity. Okay, and you have it here. So you have an average of, let's say, 8, which is not optimal. It's below the buffer, but it's not optimal. Okay, so it should be better to have something finer. So see that you have all this here. Also, you have the vectors here. So in this one, plot this one, you have all your vectors there. I want to point out, see here that you have the recirculation region here. So you have the secondary string, and see this enter, and you have this recirculation. You have another one here, smaller, but you have it there as well. See. So this is the turbulence model in action. So you run this one, probably here also another small one. So you run this one laminar, you won't get this, or you will get very different behaviors. Okay, it's likely laminar is the wrong solution, but it's not wrong because the laminar equations are wrong. It's wrong because we have seen for the laminars are the exact Navier-Stokes equation, DNS. You need extremely defined meshes. You need to go on a steady to capture the right physics. Okay, so at this point, what I want to do now is to move to plops. Okay, so see that I created this line that I show you here. So now all that sampling, whoops, is done in that line. So as I go here, you see that already those plots has been created. So see here that plot 1, you have the classical plot here. Okay. So this plot is y plus, u plus against y plus, okay? So I already computed these quantities, and let me revisit that, okay? So here you see, remember in custom field functions as well, you compute those quantities. So let me go here. So how to plot those profiles, remember, you need to pick up a location in your domain. Preferably it's a location where the flow is fully developed and is attached. Okay, sampling wall shear stresses, and then this line normal to the wall, sample the velocity. Okay, and remember, starting from this point, the coordinates are 0, 0. So it's distance normal to the wall. So be careful when doing that. So that's all that you need to do to do this plot. No, the y plus u plus, and then it's logarithmic scales. You have it there. But here, just to show you, name it in custom field functions. You have it here, so you know how to create it. Okay, we already have done this. So see here that I'm computing u tau. Okay, then this is this distance normal to that point. So I know that the coordinate at that point is 0.4 minus x. So I translate it to x, or well, usually it's a good idea to put it also an absolute value because you want positive value. Y plus, compute it here. And then your u plus. Okay, so here you create those monitors. Okay, and that's all. Okay, so at this point, for instance, let's do this plot, and remember that we can overlap here the theoretical profile. So again, let me go. So if you download the cases, okay, you will find in Fluent case, as you enter here, you see that you have the ASCII validation data. Let me copy this folder, and I will put it here. I want to access, so this is a standard data for me that I always put in cases. So you see that doesn't matter the physics, whatever, everything has been normalized, so you should be able to reproduce those profiles. So load file, and let me open this tree, this and this. Okay, I'm plotting and see that what we have. Okay, so there is a shift there, but remember what it was mentioned, that you have the secondary string, you have all those effects, the mesh is not perfect. It's something that I will expect, but the importance is that kind of you have similar behaviors, okay? So likely is that if you go and you have a much finer mesh, you will be able to reproduce this one, probably with a small shifting, and here you will have the differences, okay? But as you see, something a result that it is acceptable, okay? So see that in this case, in this point that you are sampling, see that you are sampling a critical point where you are in the buffer layer, about 20. Okay, so this is not the best location to do the sampling, the one I chose there. Okay, so as you keep going with the plots here, now we have this one. So again, now all these plots will be y plus, normal to the wall, and then you have velocity. So this is velocity dimensional. See that you have the secondary string, and then the other one passing, and so on. You keep putting your plots. Okay, so here you have the turbulent kinetic energy. So see that you have a peak here, and then you have this. Okay, another peak here corresponding to the secondary string, the other one. You plot here, again, dissipation, that it will be maximum at the walls in the viscous layer there, not when all the turbulence should be dissipated. So see here that you have a maximum there. This is the production. Later we're going to talk about this one, but this is production of turbulence, okay? So you have that term also. And you go here, and this is the wall shear stress, okay? So you have the wall, okay? So here you have a peak here. So this is the location. So actually, this case, by the way, as you are running your case, also you should recompute your shear velocity, because let me reopen here, manage. So in this case, the shear velocity U tau is computed using this value, which is very different from the one that we have computed, okay? So this should be corrected, okay? So be careful that then you should recompute this quantity, okay, U tau. So you should recompute it. So let me do it just to show you. Okay, let me recall here. So let's do square root of this quantity. Let's say that is 3.47 divided 1000. Okay, define. Okay, manage. Okay, so also let me erase this one, and let me rename this one. Okay, sorry, here, U tau. Okay, so I rename this one. Okay, so if I go now and let me create another report here. Okay, so if I go here, surface integral, I want it in line 1. So see that if I compute facet average, it's giving you the facet average there. But you can go, for instance, and get the maximum y plus in that line. So here I want this custom function, and just give me the maximum. So this is your U tau value there, 0.058, okay? Okay, so at this point, let me go back here. And this one has been recomputed with the new value. Go here, and let me plot this strip. Okay, so see that was a slight improvement, a slight difference, but important. Always these quantities are local, depends on where you are sampling and depend for the current state. So you need always to measure that quantity and plot it there. So then you have these blobs or velocities. Okay, so there is much to do. Later in the 3D case, we're going to see some other plots. So basically this was this advanced plotting. So try to reproduce these plots. Okay, and you have there the solution. So as you see, this is very standard. Okay, it doesn't matter the geometry case, you should always be able to reproduce and be very critical. Okay, because sometimes you can get strange conditions and you may say, oh, but I'm not reproducing my profile. Now remember, you can have many flows entering, interaction with top wall, or you can have, well, separation, which is not the recommended. So be careful now and look at where you are sampling, look at what are the flow conditions and what is happening there. Okay, so this is all for this current state. Save it, by the way, because starting from here we are going to do something else. So I will call it case 1. Okay, so we're going to do something nice, that we're going to use adaptive mesh refinement. We're going to talk about this in the next video. So thank you for your attention. See you later.